Hi, this is chapter 23 on carbonyl condensation reactions. Let's review just quickly the ways we've seen carbonyls react. They've acted as electrophiles because the actual carbonyl carbon itself is partial positive. A nucleophile attacks it and kicks electrons up onto the oxygen. Okay? We saw that as far back as the ketones and aldehydes chapter. More recently, we've seen carbonyls act as nucleophiles, specifically at the alpha carbon, right? When we deprotonate the alpha carbon, we end up with this enolate ion, one resonance structure of which is the C double bond with the O minus. So the O minus can push its electrons back down in. The pi electrons in the CC double bond can attack an electrophile, and we'll have a new attachment at the alpha carbon. So two ways that carbonyls can react. Important to know they're at different places, right? Carbonyl carbon itself is electrophilic, but the alpha carbon can be nucleophilic. In this chapter, carbonyl condensation reactions, an enolate nucleophile attacks a carbonyl electrophile. So we've got one carbonyl compound attacking another carbonyl compound, and we form a new carbon-carbon bond as a result. So let's take a look. This is one example of a general mechanism of a carbonyl condensation reaction. We start by deprotonating an alpha hydrogen, right, just like we've done before to make an enolate ion. That enolate then comes and attacks a carbonyl of a different compound, forming a new carbon-carbon bond, right, with an alkoxide tetrahedral product there. One thing that can happen is that alkoxide can just get protonated, and we can end up with a beta-hydroxy carbonyl compound, right? Here's beta-hydroxy. There's our original carbonyl. Another thing that can happen is if, say, we have our enolate, let's get a better color here. Here's our enolate, O minus. That enolate could attack a carbonyl that has a leaving group attached. C double bond O. Right, O minus comes down. The alpha carbon attacks the carbonyl of the electrophile, right? That comes up. It'll come back down and kick out the leaving group, right? Giving us something like this. C double bond O, CH2, C double bond O. Okay? So having that leaving group attached gives us a beta dicarbonyl compound. Or one more thing we can do is if I have a enolate, we can do a conjugate addition. Right? Here's an alpha beta unsaturated carbonyl compound. Enolate comes down. Alpha carbon of the enolate attacks the beta carbon of the unsaturated compound, and we end up doing a conjugate addition. So we'll do this mechanism in detail later on, but what we end up with is C double bond O of the original enolate. Here's the original alpha carbon. Here's the beta carbon, alpha carbon, and carbonyl. There we go. 1, 2, 3, 4, 5. 1, 5. Dicarbonyl. Okay? So, three options for products that can be made. Attacking a carbonyl with no leaving group gives us a beta-hydroxy carbonyl. Attacking a carbonyl with a leaving group gives us a beta-dicarbonyl. Okay? Performing a conjugate addition gives us a 1,5 dicarbonyl. That's our framework of reactions that we'll be studying in this chapter.